In section 2.6, we have rational functions and asymptotes. So what we're going to look at is the domains of rational functions, finding vertical and horizontal asymptotes of graphs, and using rational functions to model and solve real-life problems. So kind of an introduction to rational functions. A rational function can be written in the form of a ratio of polynomial functions. So the numerator and the denominator both have to be a version of a polynomial function. And then in general, the domain of your rational functions are all real numbers except the x values that make the denominator 0. So in this first example, if we need to find the domain of 1 over x and discuss the behavior near any excluded values. So if we look at this table, we know that the domain, I'm still in my highlighter, that the domain of 1 over x, the x can't equal 0. So we would say our domain, our reals, not equal to 0. Or if we were using interval notation, we would say negative infinity to 0, and then 0 to infinity. And so if we look at the table, as our x value comes in here from the left, these negative numbers, and we get closer and closer to 0, if you notice our y values go towards negative infinity. So we would say that as x approaches 0, our function, f of x, approaches negative infinity. And the notation we use, x approaches 0, if we put a little negative sign after it, that means from the negative direction or from the left. And then here, as we're approaching 0 from the right, our y values are getting infinitely large. So as x approaches 0 from the right, our y values, or f of x, is approaching positive infinity. And hopefully you were thinking about your graph of 1 over x that looks like this. And so graphically, what we're talking about here is that as x is approaching 0 from the left, our y values are going to negative infinity, and as we're approaching 0 from the right, our y values are going back up to positive infinity. So your vertical and horizontal asymptotes are when your x values are approaching some particular number and your y values increase or decrease without bound or go to positive or negative infinity, then we call that a vertical asymptote. So x equals 0 is your vertical asymptote, right? A lot of times if we're graphing, we draw that sketched line there. Your horizontal asymptote is what do the ends of your graph approach as your x value goes to positive and negative infinity. And so in this case, our horizontal asymptote would be the x-axis, or we could say y equals 0. And that's what we're talking about in here. So from the figure, you can see that the graph has a horizontal asymptote at the line y equals 0. That means that it just approaches that line as your values get towards their ends. So kind of that formal definition for vertical and horizontal, x equals a is a vertical asymptote. So one thing you have to remember is that when you write vertical and horizontal asymptotes, you need to write them as x equals a or as a y equals b. So an asymptote is always written, so write as equation. So you always have to write them as an equation. You can't just write them as a number. So if we have f to be a rational function where you have these two polynomials, n of x over d of x, and if they have no common factors, so if you were to factor them and there's nothing common in the numerator or denominator, then the graph will have vertical asymptotes at the zeros of the denominator. And then the other thing is that the graph has at most one horizontal asymptote determined by comparing the degrees. So the way that you find the horizontal asymptote is that if your degree of your numerator is less then the degree of the denominator, then the x-axis is a horizontal asymptote. So the degree, this is for if the degree of the numerator is less than the degree of the denominator. So when you look at it, if your denominator has a higher degree, then your horizontal asymptote will be y equals 0, or the x-axis. If they have the same degree, then it's whatever the leading coefficients simplify to. So if you had something that was like y equals 3x squared plus 2x plus 1 minus 1 over 4x squared plus 7, then if you notice, they have the same, their leading terms have the same degree. So whatever those simplify to, in this case 3/4, y equals 3/4 would be your horizontal asymptote. And then the last one is that if your numerator has a higher degree, so this last one is if the numerator has a higher degree, then there is no horizontal asymptote. So in this example 2, finding vertical and horizontal asymptotes. So let's start with A. And if we're looking for our vertical asymptote, the first thing you want to do is factor it if possible, which in this case, we can't factor it anymore. So our vertical asymptote will come from when our denominator, 3x squared plus 1, equals 0. And so if you were to try to solve this, 3x squared equals -1, or x squared equals -1/3, hopefully you get to a point where you realize you're going to get an imaginary number, which would mean that there's no vertical asymptotes. Now, if we were looking for the horizontal asymptotes, let's always look at those terms. And remember, if the degree of the denominator is higher, so in this case, we have a higher degree in the denominator, so the horizontal asymptote is going to be the x-axis, or you could say the line y equals 0. So for part B, if we go to the vertical asymptote, again, let's factor it. So if we have 2x squared, and it would factor into x plus 1, x minus 1. So we don't have any of the same factors in the numerator and denominator, which means that our vertical asymptotes will just be whatever would make the denominator equal to 0. So x equals -1 and x equals +1 would be our vertical asymptotes. So now for our horizontal asymptotes, if we compare 2x squared and x squared, they have the same degree. So that would simplify into just 2. So we would say y equals 2 would be our horizontal asymptote. All right, so our application, there's many ways and examples for asymptotic behavior in real life. For instance, this next example shows the vertical asymptote can be used to analyze the cost of removing pollutants from smokestack emissions. So we have a utility company that burns coal to generate electricity, and the cost in dollars of removing P% of the smokestack pollutants is given by this equation for values 0 to 100 because P is a percent. So use a graphing utility to graph this function. You're a member of a state legislature, and it's considering a law that would require the utility company to remove 90% of pollutants from their smokestack. The current law requires 85%. How much additional cost would the utility company incur as a result of the new law? So in this case, they want the new law to be 90%, where the current law is 85%. So what I want you to do is in your calculator, in your Y1, you're going to have 80,000, and in this case we're going to say x, but x is our p-value, divided by 100 minus p. And once you have that in there, then go to your table set, and we want to see what the cost is currently to remove 85%. So in your table set, have your table start at 85 and have your change in table be 1. And then go to your table, and so we know that the cost when we have 85% removed is $453,333. And then if we want to compare that to the cost at 90, scroll down on your table, and the cost to have 90% removed would be $720 million. And so the question wants to know how much additional cost. So if you take that 720 million, not million, thousand, sorry, 720,000 and 453,000, and subtract your 453,335, you get that the difference in cost would be $266,665 more to remove those extra pollutants. One other thing I want us to look at with this is if we were to look to see if there was any type of asymptotes, right? So in this case, if we were to look at this, just considering the asymptote, your vertical asymptote is when the denominator equals 0. So in this case, it would be P equals 100 would be your vertical asymptote. So that means you can't remove 100% of the pollutants, like it's impossible. Your horizontal asymptote would be at some point, is there a cost where it just levels out? And so to do your horizontal asymptote, we actually need to put this in standard form. So our 80,000 P, and put that over our negative P plus 100. And so now when you compare those terms, your horizontal asymptote is going to be that C equals negative 80,000.